All right, let's talk about a huge shift happening in quantum computing. For years it's felt like this far-off sci-fi thing, but now it's actually getting a job. I'm serious. It's becoming a real tool that chemists, financial analysts, and engineers can use to solve problems that were just impossible before. So how are we making this giant leap from the lab to a live application? Let's get into it.
So here's our game plan for today. We're going to start with what it even means for quantum to become a practical utility. Then, we'll peek under the hood at the serverless cloud that's making it all run. After that, we'll check out the pre-built toolkits that make it easy for anyone to use, see the crazy fast new hardware that's powering it all, and figure out how it plugs right into the supercomputers we already have. And of course, we'll wrap up by looking at what's next in this quantum revolution. It's going to be fun.
Okay, first up, what does it really mean for quantum to get a job? I mean, for decades, this has been a super fascinating but mostly theoretical field, right? Well, that's all changing. It's moving from a science experiment to a practical tool that industries can actually use to solve specific real-world problems. The kinds of problems that have been completely out of reach until now.
And this really gets to the heart of it all. Think about it. The goal isn't to make you a quantum physicist. Not anymore. It's all about empowering the experts we already have. The chemists who really get molecules, or the financial whizzes who live and breathe markets. It's about giving them the power of quantum to solve their problems. It's bringing the power to the person who needs it.
This brings us to this really big idea, quantum utility. So instead of thinking of a quantum computer as this big, standalone thing, I want you to imagine its processor, the QPU, as a superpowered coprocessor. It works right alongside a traditional supercomputer, and its whole job is to tackle the parts of a problem that are just insanely complex, the parts that even our fastest classical machines could never handle. But how do you make this quantum utility a real thing? Well, it all starts in the engine room, a brand new serverless quantum cloud. You can think of it as the operating system for this whole new era of computing, connecting you to the hardware totally seamlessly.
And the core of this whole thing is a technology called Qiskit Serverless. And this is a total game changer. Here's why. It means you can send a really complex job, one that needs both quantum and classical computers, up to the cloud, and then just walk away. Seriously, you can shut down your laptop, go grab lunch, and that computation will just keep running for hours or even days without you having to stay connected at all.
So this is what that journey looks like for your job. It starts with your code, right? It zips through a secure gateway, and then this really smart scheduler finds the perfect classical and quantum processors for the task. And finally, this powerful framework called Ray acts like the ultimate traffic controller, managing all the different moving parts of the computation to bring you back a final answer. The whole process? Completely managed, totally seamless.
Okay, so we've got this powerful cloud infrastructure in place, but how does it use her? Let's go back to our chemist. How do they actually use it without needing a PhD in quantum software engineering? Well, that's where the Quantum Toolkit comes in, with these awesome pre-built apps designed to make it super easy.
The answer is something called Qiskit Functions. And honestly, the best way to think about them is like specialized apps in an app store. They take care of all the incredibly heavy lifting in the background. I'm talking translating your problem into quantum circuits, optimizing them for the exact hardware, running the calculations, and then sorting through all the noisy results. All you have to do is provide the input, and boom, you get the answer back. It's that simple.
Now, what's really cool is that these functions come in two main flavors for two very different types of users. On one side, you've got circuit functions. These are for the quantum researchers, the folks who want to get their hands dirty and design their own circuits, but need help dealing with all that tricky hardware noise. And then, on the other side, you have application functions. These are for the domain experts. Our chemist can just pop in a molecule and get its ground state energy back without ever having to even think about a single quantum gate.
And check this out. Here is a powerful example of this in action. Researchers are using one of these application functions to team up an IBM quantum processor with Fugaku, which is one of the world's fastest supercomputers over in Japan. And together, they're tackling this incredibly complex problem of accurately simulating new drug compounds, a huge step in discovering new medicines. And the impact? It's just staggering. This isn't just, a minor speed up. We are talking about taking calculations that would normally run for years on a classical supercomputer alone and getting them done in a matter of hours. This is it. This is the promise of quantum utility, and it's being delivered today. Of course, all this amazing software needs equally powerful hardware to run on. And on that front, the quantum processors themselves are in the middle of their own revolution, which is letting us tackle bigger and bigger problems. A perfect example is IBM's new Nighthawk processor. It's switching from an older, heavy hex layout to a new square topology. So what does that actually mean in plain English? Well, think of it like a city grid. The old layout had fewer streets connecting all the buildings, which meant data sometimes had to take this long, roundabout path. The new square layout adds a ton more direct connections. This cuts down on the number of extra steps, or what we call overhead, needed to run a program. The result? You can run 30% more complex circuits with way less error.
This hardware upgrade also means a huge boost in raw speed, which we measure in something called CLOPS. That's circuit layer operations per second. Basically, it's a measure of how many slices of a quantum computation you can run in a single second. And after being pretty stable for a bit, that number is about to take a massive leap forward.
And that huge jump in CLOPS, it translates directly to this incredible number. By the end of 2025, those big utility-scale experiments will be running 100 times faster, 100x faster than they did back in 2023. That's the kind of acceleration that turns these multi-year research projects that seemed impossible into something you can get done in just a matter of weeks.
Okay, so we have the software and we have the hardware. But for quantum to become a true utility, it can't live off in its own little silo. It has to integrate seamlessly, and it has to speak the native language of the world we already have, the world of high-performance computing, or HPC.
And IBM has been busy building the bridges to make exactly that happen. There's a universal translator, so the standard software that schedules jobs on supercomputers can now manage quantum hardware too. There are special plugins that let a system admin treat a quantum processor just like any other computer resource. And for the scientists who need every last drop of performance, they can now call these quantum functions directly from their high-speed C++ code, bypassing any potential slowdowns.
This really helps put IBM's strategy into the bigger picture. While a competitor like AWS Bracket basically acts as a gateway to lots of different hardware, and Azure Quantum is focused on its unique Q-sharp language, IBM is betting on a totally different approach, a deeply integrated full-stack solution. Everything from their own custom-built processors all the way up to these super user-friendly application functions.
Now, everything we've talked about so far, this whole new era of quantum utility, is incredibly powerful. But really, it's just a stepping stone to something even more revolutionary. So let's take a look at the road ahead, to the next quantum leap.
The roadmap has two huge milestones coming up. First, in 2026, there's Flamingo, a processor designed to be modular so you can link them together to build much bigger systems. And then, in 2029 comes Starling, which is aiming for the holy grail of this entire field, true fault-tolerant quantum computing. Starling is designed to use what are called logical qubits, which are actually groups of physical qubits all working together as a team, constantly checking for and correcting their own errors. This makes the whole computation incredibly robust. You see, the key to fault tolerance is this constant race against time. You have to find and correct errors faster than they can pile up and wreck your calculation. And in a major breakthrough, IBM has already proven this is possible. They've demonstrated real-time error decoding, a critical milestone they hit a full year ahead of their own ambitious schedule. That's huge.
So, what's the big takeaway from all this? It's that quantum computing is finally graduating. It's moving beyond being just a lab experiment to become a standard tool in the world of high-performance computing. The question has totally shifted. It's no longer if this stuff will ever be useful. The much more exciting question now is, with this incredible new power at our fingertips, what previously unsolvable problem are we going to tackle first?